Good morning, Mr. Chichtai, Anratanak, Mesa Tang, and David Shamroin, Purun, Sotiarit. Chichtai, can you hear me?
Yes, sir.
Okay. Guys, good to see you again. Unfortunately, I had to change today's class to online mode. All of a sudden the weather changed a lot and the teaching in the air-conditioned room, it may be a bit risky, and we will see, okay? But on Thursday, as you know, you'll have quiz at the campus, hopefully, if there will be no any big change. And next week, we will also continue in the campus on Tuesday. So today, we are going to have class here online. And guys, last time in our last class, we talked about tangent planes and differentials. This differential, we didn't talk much, okay? Actually, there will be no question from this differential part. But if you are given any function of two variables, you should be able to write the equation of a tangent. If you remember, what is that equation? It is f x, right, at point A, B. Let's say it's x minus x sub 0 plus f y, y minus y sub 0, and minus z minus, what is it? The given point, that's equal to 0. Anyway, and also you have to be able to write the norm or normal line to the plane at the given point. So that's what we did in 14.6, and also linearization, because we linearize sometimes a function if it is so complicated to evaluate. So today we are going to talk about extreme values and saddle points. And also we have Lagrange multipliers. One topic is left, but if I just wait to finish this 14.8, and we are going to lose a lot of time. That's why let's have actual quiz, and soon also you are going to have midterm. In midterm, I will involve more questions from chapters 14 and chapter 15. Okay, so today we will talk about extreme values and saddle points. The extreme values, again, if you remember when we studied, what is it, derivatives, right? One of the most important application of derivatives is to locate the function's extremums. Extremums means that where the function has maximum value, where the function has minimum value, or local maximum and local minimum. Okay, and this idea is very important in optimization problems, right? Especially, for example, to minimize the cost and to maximize the volume and blah, 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 this kind of stuff. So, and also some actually application we'll see is about the temperature. For example, if you are heating a kind of plate, maybe rectangular or circular, but usually here it's not circular, it's rectangular. Okay, so if you're heating this from one point, all right, then there will be kind of heat distribution among the plates. And if the temperature on the plate is given by some function of maybe 2 or 3 variables, right, at the time we may wonder where the temperature is the highest, where it is lowest. Anyway, so today we are going to talk about derivative tests for local extreme values and absolute maxima and minima on closed bounded regions. And in quiz also I will include 14.7. Right? That's why you have to practice a few questions from this section. So now, as you see in the picture, right here, we are given the graphs of a function of 2 variables. And as you see here in the first one, if you just draw the tangent, it's just sitting on the tangent line. So actually this function has a local minimum right here. And how about the second one? The function, right, if you just take some region, okay, or a kind of open disk, actually I can just show one value of the function that is greater than all of the neighboring, let's say, values of the function, which gives us the idea of local maximum. And also, actually, if you remember, when actually talk about a function of single variable, right? First, we have the differentiate, find this derivative, right? And find this what is it? Critical points. But critical point, it just helps us to locate maximum or minimum, but that's not enough. And also, actually, the point may be a point of inflection, right? As inflection, there the function doesn't have minimum value or maximum value. If you just remember, for example, here this kind of function, right? And if you just draw here actually the derivative of the function is 0. But the function doesn't have local minimum or local maximum, because over the whole interval, right, the function's graph is, what is it, rising, or the value of the function is increasing. And how about when we talk about a function of two variables? Actually, we call this a saddle point. Why saddle point? Because you see here, the graph looks like a saddle on the, what is it, a bike or a horse, right? And that's why it is called saddle point. If you just move in this direction, it has minimum, right? Local minimum. If you just follow in this direction, it has local maximum. So you see here, it doesn't have any local maximum or minimum at this point. And such points are called saddle points. Now we will study under what conditions we will have saddle point, under what condition we have local minimum and local maximum. So again, we know that when we talk about the application of derivatives, the first theorem says that, if you remember, if we are given a continuous function in a closed interval, right? So in a closed interval, if you're given a continuous function, then it must have local maximum, actually global maximum, and also it must have global minimum. So that is the most important, or one of the most important features of continuous functions. So continuous function of two variables assume means take on or takes on extreme values on closed bounded domains. We see in this section that we can narrow the search for these extreme values by examining the function first partial derivatives. Okay, narrow means that, okay, if you know that, then how do you find this? Because we are talking about infinitely many points, right? We cannot actually just check one by one. So what is the shortest way that takes us, or that helps us to find these extreme points? So a function of two variables can assume extreme values only at domain boundary points or at interior points where both first partial derivatives are 0, or where one or both of the first partial derivatives fail to exist. It's very similar to a function of single variable. And if you're talking about a function over the certain, or is it, closed interval, right? If you remember, first, to find it is local maximum or local minimum, we have to differentiate, right? And that's equal to 0. And solving this equation, we can find it is critical points. And after that, we have to check, okay, evaluate its value at endpoints and at critical points. And we can compare these values, okay? Then which one is the biggest? It gives us global maximum. And the smallest one gives us global minimum. However, the vanishing of derivatives at an interior point AB does not always signal the presence of an extreme value. So the surface that is a graph of the function might be shaped like a saddle right above AB and cross its tangent plane there. If we just talk about, what is this, the saddle point. So we may have actually the partial derivatives may be equal to 0 at a point, but that's not enough. As it says here, it may be a saddle point, that which means that the function doesn't have neither local maximum or local minimum. So now let's start with this definitions. Definitions, again, is very, very similar to the definition of local maximum and local minimum. So now let f of x, y be defined on a region R containing the point AB. Right, you're talking about kind of region. Okay, let's say this is our region. Let's say this R, and here we have given a point A and B. Okay, then f a b, right, is the local maximum value of f. If f of a b is greater than or equal to f of xy for all domain points xy in an open disk centered at ab. So that means that now if you just take some open disk, okay, that contains what is it, the point AB, or the center. When you just compare this AB gives us the greatest of these values, then we say that this f of AB is the local maximum of the function f. In a similar way, f of AB is a local minimum value of f if f of AB is less than or equal to f of xy for all domain points xy in an open disk centered at AB. Okay, it's a kind of hat, right? Maybe the top part of the hat, or if you just invert this, the bottom of the hat. Actually, these are the points that gives us the local maximum and local minimum. And of course, to find the global maximum, actually our what is it, region domain must be bounded. Bounded means that it should not go to infinity. Then we can compare the values. Okay. Here's some example local maxima, no greater value of f nearby. Let's see here, the first point, local maximum, the second point, local maximum, and that's the deepest part of the ocean maybe, so actually locally, that is local minimum, no smaller value of f nearby. Okay, that's why it's called locally, comparing to some neighboring points that gives us the maximum value. First derivative test for local extreme values. So it's like, what is it? The first derivative test also for single variable function. If you remember, if you are given f of x, right, and it has a local maximum or minimum value at an interior point A of its domain, if the first derivative of the function is equal to 0. This gives us the local, actually critical points of the function in the interval. But here we are talking about a function of two variables. So it says that if f of xy has a local maximum or minimum value at an interior point AB of its domain, and if the first partial derivative exists, actually first partial derivatives exists there, then the fx AB is equal to 0 and fy of AB is equal to 0. That means that actually, what does it mean? So this local maximum, local minimum means that at this point AB, right, we can draw a tangent plane to the surface or to the graph of the function, which is parallel to the xy plane, right? So that means that actually here, when you draw this, if we just take in some open disk centered AB, if we just compare all the points, it will be lying either under this shelter or plane or above this shelter or this plane. Okay, this is how we are defining, I mean, this local maximum and minimum. Actually, this is the theorem and proof is simple. Just here, what we are trying to say here is the geometric interpretation of this theorem is at this point. That means that where fxab is equal to 0 and fyab is equal to 0. If it is so, that means that at the point AB, we can draw a plane, okay, tangent plane that is parallel to the xy plane. Okay. Proof is, you can just consider at the time, for example, the function, if you just fix this fxab is equal to 0 means that I can just actually, for example, label this function f, x, and b. Okay. So now if you differentiate this f prime, g prime of x, that's equal to f, x. Here we have xb, right? And it says that if the derivative is equal to 0 here, that means that here f, x, a, b is equal to 0. Right, g prime of x. That gives us the critical point. In a similar way, if h of x is equal to our function is f, now we are differentiating this with respect to y. This is y. It should be x. And it should be y. Now from here, saying that this h prime of y, right, which is equal to f, y. Here we have a, y. And also that's equal to 0 at this given point. That is h prime of b, that's equal to f prime a b. Okay, that's equal to 0. So now using these values, we can actually write the equation of the tangent plane at the given point AB. And what is the equation of the tangent? That is f x AB. And here we have x minus a plus fyab, and here we have y minus b, and minus here we have z minus f at point AB. So that is equal to 0. This is the equation of a tangent plane at this point, right? So now fxab, that's equal to 0. Fyab is equal to 0. So since this equation is equal to 0, the z minus f of ab must be equal to 0, which means that this z is equal to f of ab. What does it mean? Z is our function, right? The function actually, the equation of the tangent plane. Z minus, D is equal to f of AB means that it is just a constant, right? The constant means it's like y is equal to c is a constant. What is it? It's a constant function, the horizontal line parallel to the x-axis. But here, z is a constant number means that, right, whatever x and y, it is a constant. That means that at this point, if these partial derivatives are zero there, right, we can draw a tangent that is parallel to the xy plane. So which means that it's actually there must be local maximum or minimum. If, okay, there is local maximum minimum, it must be there at critical point in the interior points. Okay, an interior point of the domain of a function f, where both fx and fy are zero, or where one or both of fx and fy do not exist, is a critical point of f. Again, it's also very similar to the critical point definition of a function of single variable. And if you remember, what kind of points are called critical points? The derivative of the function there should be equal to zero, or the derivative of the function should fail to exist at that point. Then we call this the critical point of f. Okay, and these are some examples actually in the graph. So here, PQ, that is a critical point because the derivative is equal to zero, both. And also here we have, or is some critical points at the top, which gives us local maximum or local minimum. Okay. Now let's give the definition of a saddle point. A differentiable function f has a saddle point at a critical point AB. If in every open disk centered at AB, if you just take some open disk centered at AB, there are domain points xy where f of xy is greater than AB, and domain points xy where f of xy is less than f of AB. So which means that actually there's no local maximum or minimum there. So that's the definition of what is it, saddle point. Of course, every time checking in this way is not a practical way, and soon we will give a very powerful theorem and use that theorem to find or determine the local extremum of the function. Anyway, the corresponding point a, b, f of a on the surface z equals f of xy is called a saddle point of the surface. See in the picture, see here minimum in one slice, right? If you just slice in this way, that is, what is it? That is cutting parallel to the z plane. But if you cut this parallel to the yz plane, it has maximum value. At this point, right, it has maximum, and also in another direction, this minimum. So that gives us the saddle point. Now let's start with this example. Find the local extreme values of this function. Okay. So solution to find the local extreme values, right? We need to find the critical points. So if you differentiate with respect to x, that's equal to 2x, right? And if you differentiate with respect to y, that's equal to 2y minus 4. So when 2x is equal to 0, when x is equal to 0. And when 2x minus 4 is equal to 0, when y is equal to 2. So this 0, 2, right, this 0, 2 is the critical point of this function. So it has only one critical point. Okay. So now if the question is, okay, this critical point, does it give us local maximum or local minimum? In two different ways, we can just say this. Number one is maybe algebraic way. Algebraic way is I can just rearrange and write this in this form. Here we have x squared, and this y squared minus 4y plus 9, I can write it as y minus 2 squared plus 5. And this x squared is always greater than or equal to 0. And also y minus 2 squared is greater than or equal to 0, which means that our function is always greater than or equal to 0. So which means that actually this 0.02, it gives us, what is it, local minimum. At the same time, actually it gives us global minimum because it is the smallest value of this function. But actually it doesn't have any local maximum or global maximum. So this point gives us local minimum or global minimum. Another one is, the second method is, what is this? Since we know we are trying to find that because it says only one critical point, right? I'm just going to identify it doesn't give us the minimum value or maximum value. To do this one, just evaluate the value of the function at two different points. At this critical point, 0, 2, that's equal to 0, plus 4 minus 8 plus 9. That's equal to 5. That's the critical point. At any point, for example, how about at 2, 0? 2, 0, that's equal to x equals 2, right, is 4, and y is equal to 0, 0 plus 9, that's equal to 13. So which means that if you evaluate any, actually, the function at any other different point from 0 to, you will see that it will be greater than 5, which means that actually the 0.02 is the local minimum or global minimum of this function. Okay, find the local extreme values, if any, exist of this function. So again, first, if you evaluate their partial derivatives, that's equal to minus 2x, and the fy is equal to 2y. And that's equal to 0. Also, that's equal to 0 whenever x is equal to 0 and y is equal to 0. So this critical point is the origin. I mean, 0, 0. I can just write also z component. Okay, this is just a domain point. So the 0, 0 is the critical point of this function. Okay, but how do I know that it is actually local maximum or local minimum? But now, if you just take some open disk centered at the origin, okay, any disk, it doesn't matter the radius, anything, okay. Let me just take any point. For example, here, evaluate 0, 1. 0, 1 is equal to 0 minus 1, that's equal to negative 1, less than 0. And how about 1, 0? That is 1 minus 0, that's equal to 1, it is positive. As here near this point, even you can just get smaller point, 1 is negative, 1 is positive, right? So which means that actually we have points which are greater than 0, which are points that's greater than 0. So that means that actually the 0, 0, it doesn't give us any local maximum or local minimum. And since I have just shown only 2 points, right, where f of xy is greater than f of ab, that is 0, 0, right? And the f of ba here, that is 1, that's greater than f of 0, 0, that is 0. So now we can conclude that then this 0, 0 is the point 0, 0, and also 0. Actually, that belongs to the graph of the function. That is the saddle point of this function. There, even partial derivatives are equal to 0, but it doesn't have local maximum or minimum. Of course, usually we don't actually evaluate this like this. We will use theorem. Okay, now that is the most important theorem of this section to find what is the local maximum and the minimum. Second derivative test for local extreme values. And its proof is given at the end of this section, but we will see. Okay. Now here, let's try to apply this formula or this theorem to evaluate or to solve some questions. Suppose that f and its first and second partial derivatives are continuous throughout a disk centered at AB. And that fx AB and fy AB is equal to 0. That's the first condition because it must be a critical point. Then we can actually search for either it is local maximum or local minimum. Now it's saying that the first one, f has a local maximum at AB if fxx, the second order derivative of f with respect to x, is less than 0, and fxx fyy minus fxy squared is greater than 0 at AB. So this one is a special expression. Okay, this one is Hessian function. How is it written? Actually, this Hessian function is written like this: Hessian function of f. Okay, and I don't know, the notation may be a bit different. It is a determinant. Actually, here we have fxx, fxy, and here we have fyx, fyy, and we know that these mixed derivatives are equal, right? fxy or fyx, they are equal. So I can just write xy or yx, doesn't matter. So if you evaluate this determinant, that's equal to fxx times fyy minus fxy times fxy. That's just equal to square. Okay. So Hessian determinants, you can just also remember like this. And it says that f has a local maximum at AB if fxx is less than 0. This less than 0, you can just remember that actually it's what is it, concave down, right? Actually it's our shape concave down. So there we have local maximum if also our condition here is fxx fyy minus fxy squared should be positive. F has a local minimum at AB if fxx is greater than 0. And again, this Hessian determinant is greater than 0. And how about the saddle point? Actually, if this fxx fyy minus fxy squared is less than 0, it gives us the saddle point of the function at AB. And how about if it is equal to 0, then the test is inconclusive. In this actually case, we must find some other way to determine the behavior of f at AB. That means that maybe you can just make some different adjustment or use some different methods. Okay, that's it, or algebraic way. So now let's apply this immediately to this question. After this, maybe, okay. So find the local extreme values of the function. First, we have to find it is critical points. If you differentiate this with respect to x, here we have y minus 2x minus 2. That should be equal to 0. If you differentiate this with respect to y, is equal to x minus 2y minus 2. That's equal to 0. Now we have a system of linear equations, right? If you solve them together, the first one is minus 2x plus y is equal to 0. The second equation is x minus 2y is equal to 2. The first one is also 2. Okay. So now if you multiply the first equation by 2 and add to the second equation, minus 4y plus x, minus 4x plus x, that is minus 3x. 2y plus minus 2y is 0. Actually, 4 plus 2, that's equal to 6. So here, x is equal to negative 2, right? So if x equals negative 2, how about y? It is negative 2, 4, take to the right-hand side. Y is also equal to negative 2. So these are the critical points of this function. Negative 2, negative 4, 0, negative 2, again 4, 0. That's correct. Okay. So that is the first part of this problem. Let me just write here, first part. The second part is we have to find fxx, fxy, right? And what is fxy? And here we have fx, differentiate one more time with respect to y, that's equal to 1. And how about fxx? fxx is equal to -2. It's already constant. That's why we don't have to evaluate at with critical point. How about fyy? Fyy is equal to -2. Now, if you evaluate this, fxy fxx fyy minus fxy squared. Fxx, it is -2. Fyy, it is also -2 minus fxy squared, that is 1 squared, which is equal to 4. 4 minus 1, it is 3. It is greater than 0. So now, also as see here, if you notice, here we have f, right? Here we have also fxx. It is less than -2. -2 means that actually, again, it's just concave down. We can just understand like this, concave down. So that means that here then the function has local maximum at the given point. So f has local maximum at -2 and -2. Okay, let's continue. Another example. Okay, then we'll have break. Find the local extreme values of this function. Draw a line here. Okay, first, to find the local extreme values of this function, we need to find it is critical points. So here we have fx, that's equal to -6x squared plus 6y. That should be equal to 0. And how about fy? If we differentiate with respect to y, it is 6y minus 6y squared plus 6x. That's equal to 0. It should be just 6x, right? The first part. So now we have to solve the system together. From the first one, -6x plus 6y equals 0, which means that's actually, which gives us that y should be equal to x. So now if you substitute into the second equation, right, and also divide both sides by 6, it is 6y, okay, minus 6y squared, it is 0, 6x. That's correct. Divide both sides by 6 or -6. So here we have y squared minus y, and x is equal to y plus y is equal to 0. Six y, 3y squared minus 2y cubed minus 3x squared plus 6xy. If you differentiate with respect to x, minus 6x plus 6y. With respect to y, 6y minus 6y squared plus 6x. Okay. Okay, from here, what do we get here? If you solve this equation together, and the solution is 0, 0, and this is the critical point. Okay. So now, let's find fxy. Fxy is equal to, differentiate one more time, that's equal to 6. And fxx, and that's equal to -6. Fyy, that's equal to 6 minus 12y. 6 minus 12y, right? And at 0, 0, at critical points, we can just evaluate this. fxy at 0, 0, that's equal to 6. fxy at 0, 0, not xy, xx is equal to minus 6, that is less than 0. Okay, fyy at the critical point again, that's equal to 6 minus 0, it is 6. So now if you just evaluate this Hessian determinant, that is fxx, that is minus 6, xy, it is 6, and xy, it is 6, and yy, it is 6. So that is equal to minus 36, that's equal to minus 72. So which is less than 0. So if it is less than 0, then the given critical point must be, what is it, a saddle point. Okay, guys, that's it for this section. Let's have some rest, maybe 10 or 15 minutes. Okay, we will continue our class at 10 o'clock. In our next class, we'll talk about absolute maxima and minima on closed bounded regions. And that's it. See you after at 10 o'clock.